Alright, hello everyone. My name is Ross, and welcome to my tutorial on how to do code coverage analysis for the Wally processor. Alright, so as with any Wally setup, the first thing you need to do is make sure you run the setup file. So I'm assuming that you have already done a git clone of the repository. So just as a quick refresher, remember to run source and then setup of the setup.sh file, or CSH file if you're running C shell. I have a custom script, so just ignore that I'm using a slightly different script. Alright, so the first thing we want to do is compile the coverage tests. So to do that, we need to go to the tests/coverage directory, and we run make. And in my case, I haven't changed the tests since I've last compiled, so there's nothing to make. So we're going to go back to the root directory, and then we're going to go into the simulation directory, and then we're going to run regression-coverage. And then what this will do is it will generate it will run a portion of the Wally regression tests with model sim coverage enabled. And then it will produce a bunch of coverage reports that you can read to extract where there are potential issues where we don't have code coverage. And this takes roughly a minute to run. Okay, so now that it's done, we could navigate to the sim/cov directory. And in here we'll find a bunch of files called UCDB. So those are the actual database containing all of the coverage data. That's a non-human readable file. So that's produced by ModelSim, and it contains the actual coverage data. The RPT files are human readable files, which let you see actual useful information about the coverage results. So we can open up one of these files. For example, let's look at the LSU report. So if we come down to this one that says uncovered LSU.rpt, this will tell us what's in the LSU is specifically not covered. So if we start looking at this, right, we'll see this particular instance in the LSU, the hardware page table locker, HPTW, it goes through, and for each piece of code inside the hardware page table locker, it breaks down coverage. So the first thing it's showing us is a summary of all of the branches that exist within this module. So it's saying that there are 56 different types of branch bins, and 50 of them are covered by the regression tests that we ran, and 6 of them aren't. So the coverage is about 90% covered. And then it breaks down specifically what each one of those are. So it says on this particular line, there's these 2 particular types of coverage points, and these are the number of times they've each been tested, or each been covered. It also breaks down, so it gives you it counts ifs and elses as branches. It also counts case statements as branches. All right, so I want to pick something that's a little bit easier to understand than the hardware page table locker. So I'm going to show us an example from the data cache. So all I've done is I've searched for cache FSM and gone about 75% of the way through this report file. So now we're looking at inside the LSU is the data cache, and inside the data cache is the finite state machine. And if we drill down a little bit further, we'll find some code coverage for something called this focused expression view for a couple of lines involving the atomics. So this one in particular that's interesting here is this line 98, and it says that this expression here isn't fully covered. And what this is it's saying if this expression comes directly from the source code. So let's pull that open. So if we go to source, and then we go to cache, and then we go to cache fsm.sv, and then we go to that specific line number, 89. We'll see we've got AMO is equal to, cache atomic bit 1 is ANDed with the AND reduction of cache RW, which is exactly what's here. And what we see here is the report of what's covered and not. And so what this is saying is the input term cache atomic M1 is covered, so that we've hit both states of that being set and not set. But what's not covered is when a cache atomic is 1, cache RW is always 1. We're never in a situation where this is where this is 0. So the hint here is saying that we've never had this condition be a 0. So that we should ask ourselves, this is the time when we should ask ourselves a couple of questions. We should be thinking, number one, is it ever possible for the RTL to produce this condition? And if it's not possible to produce this condition, should we modify the RTL to not produce this, to not have this condition in the first place? And if it is possible to hit this condition, what kind of test should we develop to hit this condition? So how can we answer this question? Well, the thing we want to look back is, well, where do these signals come from originally? So we could trace this back. So these signals come from our pipeline signals that originate from the IEU's controller. So if we go to source/IEU and open up controller, and we come down to this block here, we can see that, I'm actually going to blow this up to the full window size here and make it even bigger. We can see there's a couple of fields in here. There's an atomic field, so that's where cache atomic comes from, and then there's also this mem RW, and that's where cache RW comes from. Now, atomic, bit 1 of atomic is only ever set when we're doing an AMO instruction. So you can see here this column is only ever 1 at that time. And when that happens, these 2 bits over here corresponding to mem RW, they're also 1. So that means that in this particular scenario, whenever atomic bit 1 is 1, it also follows that these both cache RW will also be 1. So that means that our logic back here for this AMO is redundant. It can be simplified. So this could actually be reduced to assign AMO is equal to cache atomic bit 1. And we can actually reduce this furthermore, right? Because these are now the same signal. There's, this is just a simple assignment. There's no logic. But for the simplicity of this demo, I'm just going to make it this simple. We're just going to do the assignment. Okay, so with this change, now let's see what happens when we rerun. If we save this file and then we rerun our regression test. So again, this will take about 1 minute. And before it overwrites this file, I'm going to save a copy of the old report. Okay. Okay. So on the left, we'll have the old report, and then on the right, we'll have the new report. Okay, so let's see if we can prove to ourselves that we don't contain this line anymore. So let's search for this expression coverage line. Let's put these both in the same spot. So, okay. So what we can see here is, all right, here's our original line that was not covered, and that line is now missing. And if we skip down to here to this this line, it's saying line 91, this one AMO, or cache RWM 0 isn't covered completely, and that's the same expression here. So what it's saying is now this this expression is no longer being included in the code coverage. So we've reduced the code coverage surface area. So we should have fewer total number of expression coverages. So if we scroll up just a tiny bit, we should see that the total number of bins and the code coverage expressions should have decreased. And it went from 91 down to 89. So that's great. So that our code coverage increased. That's what we want to see. So that concludes the first type of code coverage simplification we can make, where we've identified impossible to reach code in the RTL. The second type, which we'll demonstrate in the next video, is where we have code that is not reached with regression tests, but should be reachable, and we need to write a regression test to actually reach that code.